Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 1. Limits and Continuity. Section 2.5. Continuity.
Lesson 1. The definition of continuity. Okay, we're leaving the concept of limits for a time, and we are going to turn to a new concept, one of our three big concepts in calculus: limits, continuity, and derivatives. We're looking now at the second big concept, which is continuity of a function. This particular section, I'm going to warn you, is a rather long section. It's really worth about 2 different sections. So we're just going to attack it kind of piece by piece and definition by definition. So continuity of a function. In order to understand this idea, we're going to start with an intuitive definition of what we mean for a function to be continuous at a point. And then the next thing we'll do is write a more precise definition of continuity that will be a careful enough mathematical definition that we can use it to prove future theorems and future concepts. Okay, I want to ask you a question. If you say, I studied calculus continuously from 7 to 10 last night, what do you mean by that? Well, when you say that you study continuously, it means that you study with no breaks. You didn't get up and go to the refrigerator and grab a Coke. You didn't pull out your Xbox and play a video game. You just studied continuously, sat there and absorbed lots and lots of information. If you were to try to somehow draw that on a graph, maybe we have time down here on the x-axis. Here's 7 o'clock, here's 10 o'clock, and this might be the amount of information that you're absorbing as you're sitting there looking at your calculus book or your notes or your homework problems. And you started out knowing some probably amount of information already, and the amount of information is going up continuously from 7 o'clock to 10 o'clock. There are no breaks in the time scale here. So the same idea is true for a function. In an intuitive sense, at least, we say that a function is continuous through a point if there is no break in the graph at that particular point. Let's look at a kind of crazy function that I have graphed down here. It's the function y equals g of x, and we'll try to pick out the x values at which this function g fails to be continuous. So we're going to be looking for x values where this function has some kind of a break in the graph. If I start along these x values, notice that when I get to the x value 3, I have a break in the graph. You could think of drawing this graph with this purple pen. When I get to the hole in the graph, I can't just draw the graph right through that point. I have to actually lift my pen off the paper, and then I can go ahead and continue to draw after that point. So we would say that x equals 3 would be a place where this function fails to be continuous. And by the way, if something fails to be continuous, we say that f is discontinuous, meaning not continuous. So this function is discontinuous at the point x equals 3. Why don't you stop the video for a moment and see if you can list any other x values where this function fails to be continuous. And remember, those are places where if you tried to draw the graph through that x value, you would have to lift your pen off of the paper. Okay, let's go ahead and work through this together. Why don't we write in down here the intuitive definition of continuity? We say f is continuous at an x value x equal a, say, if we can draw the graph through the point corresponding to x equal a without lifting the pencil or pen off of the paper. If we can draw a graph through that x equal a value without lifting our pen off the paper. I'll just say without lifting pen off paper. So if we continue along here, you notice that when I get, if I'm drawing the graph, when I get to the point corresponding to x equals 6, I have to lift my pen off the paper and then continue the graph here. So 6 will be another place where this function fails to be continuous, in other words, where f is discontinuous. Oh, I guess in this case I should say this is the function g, not the function f. So this is where g is discontinuous. How about 9? There's this kind of funny sharp corner here at 9. Do I have to lift my pen off the paper at 9 in order to continue drawing the graph? I don't. I can leave my pen right on the paper. So this function is continuous at 9 even though it has a sharp corner, but there's not a break in the graph. As I continue drawing this graph, well, I draw this piece, actually I would be drawing forever because this goes up forever, but we indicate that with a little arrow. But to get to the other side of x equal 12, I have to lift my pen off the paper, and that's because there's a vertical asymptote here. There is a break in the graph at x equal 12. So 12 is going to be the next place where my function g of x is, y equal g of x is discontinuous. So now I continue on the other side of 12, and notice that when I get to 15, I have to lift my pen off the paper to put this dot up here, and then I continue on the other side of that hole in the graph. So 15 is another place where g is discontinuous. I continue along this graph. Do I have to lift my pen off the paper at 18? No, I just leave it right on the paper, so the function has no break at 18 even though it has a sharp corner, and it is continuous at 18. So the only places where this function is discontinuous is at 3, at 6, 9 was okay, at 12, 15, and 18 was okay, it was continuous there. Okay, let's go ahead and look at the next page. And what we want to do is get a little bit more precise definition of continuity. As you can imagine, saying, oh, I don't have to lift my pen off the paper, that's not a mathematically precise definition of continuity. So that's what we're going to work towards. In order to do that, I want us to look at an example first. So in this example, what we're going to do is try to investigate the different ways that a function might fail to be continuous at a point, at a place where it might be discontinuous. So let's concentrate on this function. You can think of it as the function y equals f of x. And you notice that if we concentrate on this x value 5, is our function continuous at 5? According to our intuitive definition, it is not. So our intuitive definition said that in order to draw the graph, we have to be able to go right through the point corresponding to x equal 5 without lifting our pen off the paper. I can't do that. I have to lift my pen off the paper when I get to this hole in the graph. So we can see that f is discontinuous, and sometimes we abbreviate continuous C-O-N-T, at x equal 5. But the question becomes, why is it discontinuous? And we could say it's discontinuous because there's a hole in the graph. So I'll say because of a hole in the graph. But let's try to get more technical and think about it in terms of what would be happening with the equation y equal f of x. What happens technically to make this function not continuous at the x value of 5? Well, what would happen if I tried to plug 5 into my function? If I tried to figure out what f of 5 was, Well, I can see that to get the output value, I would go up to the graph, and normally what I do is I go up to the graph. When I hit it, I go over to the y-axis. But in this case, because there's a hole in the graph, I would just keep going upwards. I would go right through this open hole, and I would never hit the graph. What does that mean about f of 5? Well, it means that f of 5 is undefined. So the technical reason why this function, this first example, is discontinuous at 5, is not continuous at 5, is because the function isn't even defined at 5, and that creates this hole in the graph. I'm going to put a little number 1 right here, and you'll see why I label that as number 1 in a moment. So this first example is not continuous at 5 because the function isn't even defined at 5. Okay, let's look at this second example. I'm also going to call this y equal f of x. It's a new function. Is this one continuous at x equals 5? Well, not according to my intuitive definition. My intuitive definition says I have to be able to draw the graph right through x equals 5 without lifting my pen off the paper, and I can't do that because of this jump in the graph. So again, f is discontinuous at 5, but let's try to analyze why it's discontinuous at 5. In terms of the graph, we could say it's because of this jump. There's a piece, sort of a chunk of the graph here to the left of 5, then it jumps up, and there's another chunk of the graph here to the right of 5. So I'll say it's discontinuous because of the jump. That's really the reason in terms of the graph. But let's think about the equation y equal f of x and see if we can analyze what is going wrong there. Is it the same thing that happened in the graph in part A? There we said the problem was that f of 5 was undefined. So let's ask the question, is f of 5 defined in this case, or is it the same problem as before? Well, in this case, f of 5 is defined because I can find an output value corresponding to x equals 5. I start at 5, I go up vertically till I hit the graph. There's a black circle here, a black dot indicating that that's the actual point on the graph. And so it's not like this one where there's a hole in the graph, and I go over to the y-axis and I get an output value of 3. So yes, it is defined, and in fact in this case f of 5 ends up being equal to 3. So that's not the technical problem. All right, let's see if we can think about what's creating this jump though. And the problem is that as we come in from the left side, it looks like the function is getting closer and closer to this black dot. It's getting closer and closer to the value 3. Whereas if we come in from the right side, it looks like the f values, the f of x values, are getting closer and closer to 6. So that has to do with limits. Notice that if I looked at the limit of this function as x approaches 5 from the left, let's see what we would end up getting. We can do it using our graphical approach. When I get close to 5 from the left, the output values appear to be collecting around the number 3. So the limit as x approaches 5 from the left of f of x is equal to 3. On the other hand, if I were to look at the limit as x approaches 5 from the right of f of x, we said that that looks like it is going to a completely different value if I put in an input to the right of 5, go up to the graph and over. The closer I get to 5 from the right, the closer the outputs collect around 6. So the limit of my function as I approach 5 from the right is equal to 6. And what's the problem with that? That means that these two one-sided limits are not equal to each other. They do not match. And so the limit as x approaches 5 from both directions, the overall limit, What could we say about that? Well, the only time the overall limit exists is if the one-sided limits exist and are equal. They are not equal in this case, and so the overall limit does not exist. And so that's the technical problem in the graph of part B. The limit just doesn't exist. Function was defined at 5, but the limit as x approached 5 of f of x did not exist. All right, let's go ahead and go through the same kind of analysis for the function in part C. Again, I'm going to think of this as the function y equal f of x. It's a new function. Is it continuous at 5? Well, no, I can't draw the graph without lifting my pen off the paper to hit this black dot up here and then continue. So again, f is discontinuous at x equals 5. But let's try to analyze why it's discontinuous. In terms of the graph, it's because there's a hole right here in my curve and we jump up to this single point here. So I guess we could say that it's discontinuous because graph jumps at one point. But let's try to analyze it in terms of the equation. I want us to ask the same questions that we did for parts A and part B. First of all, let's see whether f is even defined at 5. So we want to know, is f of 5 defined? Well, to find that out, I just put 5 into this function graphically by going up until I hit the graph. Remember, this is an open circle, so I go right through the curved part, but I do hit a solid dot here, and I get an output value of 6. So yes, f of 5 is defined, and f of 5 turns out to be the number 6. Well, let's see if this problem that came up in part B happens. In other words, does the limit as x approaches 5 of f of x exist? So that'll be my next question. Does the limit as x approaches 5 of f of x exist? And, well, to find that out, I would really want to look at the limit from the left and the right separately. You notice that it looks like as I approach 5 from the left, my outputs are getting closer and closer to 3. And as I approach 5 from the right, what are my outputs getting closer and closer to? It looks like they are getting closer and closer to the same number, 3. And so the limit as x approaches 5 from both directions does exist in this case. The limit from the left is 3. The limit from the right is also equal to 3. And so, yeah, the limit as x approaches 5 of f of x is equal to 3. So that isn't the problem. The problem in the second example in part B was that the limit did not exist. Well, what is the problem? We said that the problem graphically was that you're going along this nice curve here, but then there's a hole in the graph and it jumps up at one point. Can we see what's happening in terms of the equation of f of x? You notice that jumping up at one point is reflected by the fact that f of 5, when we plug 5 into this function, we're up here at this black point, so we get a value of 6 for our output. But as we get closer and closer to 5 from the right and the left, we aren't getting closer and closer to 6 as an output, we're getting closer and closer to 3 as an output. So this limit here is equal to 3, but the value of the function is equal to 6. That's what's creating this phenomena where the graph suddenly jumps up at one point and then continues along the original curve. So this value here of 3, the value that the function is getting closer and closer to as x gets closer and closer to 5, is different than the value of the function at 5. These two things are not equal to each other, and that's what's forcing the function to jump up at that one point. As we come in towards 5 from the right and the left, our outputs are getting closer and closer to 3. In other words, the limit of our function is equal to 3. But the value at 5 is something completely different. The value at 5, f of 5, is equal to 6. If these two matched up, we'd be all set, but they do not match up, and that's the problem in this case. So I'm going to call that problem number 3. So in the first graph, the problem was that the function wasn't even defined at 5. In the second one, put an arrow down here, the problem was that the limit as x approached 5 of f of x didn't exist, and it created this schism in the graph. In the third example, well, the function was defined and the limit existed, but those two didn't match. They weren't equal to each other, and that meant that the function jumped up at this one point. So those are the 3 types of problems that we can run into that create a function that is not continuous at a particular value, such as x equals 5. Well, let's go ahead and look at the next page and see if we can analyze a picture similar to the ones that we looked at before. So let's now consider this particular function. I'll call it the function y equal f of x again, just so we have a name for it. Is it continuous at 5? Well, this function, you notice, doesn't seem to have any hole. It has no jump. It doesn't seem to have any kind of a problem that's making it not continuous at 5. If I were to try to draw the graph, I could draw right through the x value 5 without lifting my pen off the paper. So notice that f here is continuous at x equals 5. So no problem here. And let's go through those 3 technical problems that we talked about before. First of all, is f of 5 defined? Well, to find out, I just start out at 5 on the x-axis, go till I hit the curve, go over to the y-axis, and say, oh yeah, f of 5 is defined. F of 5 is equal to 3. I get an output value of 3. Okay, does the limit as x approaches 5 of f of x exist? Well, for that to exist, the 2 one-sided limits have to exist. So let's just check that. If I choose values that are a little bit less than 5, go up to the graph and over, I hit some y value, and as I get successively closer to 5, it looks like my y values are collecting around the number 3. So the limit as x approaches 5 from the left of this function is equal to 3. Let's try finding the limit as x approaches 5 from the right. If I choose a value that's slightly larger than 5, go up to the graph and over to the y-axis, and then choose values that are successively closer to 5, but on the right side. It looks like the y values are again collecting around the same number 3. So I'll put and limit as x approaches 3 from the right of my f of x is also equal to 3. So what does that mean about the overall limit? That's what we were actually asking. Does the limit as x approaches 5 of f of x exist? Yes, it does, and that limit turns out to be 3. Both of these one-sided limits are the same, so the overall limit is equal to that value. So the limit as x approaches 5 of f of x is equal to 3. Well, the last condition that we talked about, the last place where something could fall apart, is we said that whatever the function is limiting towards, whatever the limit as x approaches 5 of f of x, we want to know, is that the same as what you get when you plug 5 directly into the function? And what would you say in this case? Well, we said that the value of the function when we plugged 5 in was 3. The limit as x gets close to 5 of f of x is also equal to 3. In this case, notice these two numbers are equal to each other. So the answer to this question would be a resounding yes, because the limit as x approaches 5 of f of x is 3, and the value of the function when we plug 5 in is equal to 3, and those two are equal to each other. What does that mean in terms of the graph? It means that as we close in on 5, the outputs are getting close to the value right at 5. You could think of a big black dot being right here. So instead of having a hole right here in the graph or having it jump up to another particular value, we end up getting a nice smooth continuous graph through 5 because the values, as x gets close to 5, those output values are getting closer and closer to the value at x equal 5. And that's what makes this function continuous at x equal 5. So if we have a function f that satisfies all three of these conditions, the function is defined at 5, the limit as x approaches 5 of f of x exists, and those two numbers that we get are equal to each other, then that function will be, let's try to fill in that green blank there, then that function will be continuous at x equal 5. Well, let me ask you another question. What if any one of these conditions fails to hold? What if the function isn't defined at 5, or the limit as x approaches 5 of f of x doesn't exist, or perhaps these two hold but the last one doesn't hold and those two aren't equal? Well, if you remember from our examples on the last page, if any one of those conditions fails, then there's a problem with the graph and the function is not defined at x equal 5. Let me just put that last page up for a moment just to remind you, when the function wasn't defined at 5, we had a hole in the graph and the function wasn't continuous at 5. When the limit didn't exist at 5, we had a jump in the function and the function was not continuous at 5. And in the last example, the function was defined at 5, the limit existed at 5, but those two weren't equal. That condition number 3 failed to hold. And that was the case where we had a hole in the graph and the function jumped up and was a different value just at that one x value of 5. So all three of those conditions have to hold for the function to be continuous at 5. And if any one of those conditions fails to hold, then f, I'll say then, f is discontinuous at x equal 5. So let's go ahead now and we'll write down the precise definition of continuity at a point. We say that a function f is continuous at a number a, so at x equal a, if, and now we want to write down our three conditions, and we know that all three of those conditions have to hold for the function to be continuous. So it's continuous at a number a if, and we're going to say all of these have to hold. I'll say all three of these conditions hold. Say must hold. And let's write down those three conditions. The first condition we said was that the function has to be defined at whatever number we're looking at a. So f evaluated at a must be defined. I'll say is defined. In other words, we get some output value when we plug a into the function. What was the second condition? Second condition was that the limit as x approaches a, the overall limit as x approaches a of f of x, must exist. So remember, that also implies that the limit from the left exists, the limit from the right exists, and those two are equal. Then the overall limit as x approaches a of f of x will exist. And what was the last condition? Not only must f of a be defined and the limit as x approaches a of f of x exist, but whatever numbers we get for an output of f of a and a limit as x approaches a of f of x, those values must be the same. In other words, f of a must be exactly equal to the limit as x approaches a of f of x. So the value that we get in condition 1, if that holds, we'll get some output value. If it has a limit, we'll get some limiting value, and those two things have to be equal to each other. And if those two things are equal to each other and all three of these conditions hold, then our function is continuous at the number a. If any one of them fails to hold, we don't even have to check the other conditions, and that's because all of them have to hold for f to be continuous at a. As soon as we find one that doesn't hold, we know that f would be discontinuous at a. One thing I want to mention is that this is the definition that we will be using. It is the careful, precise, mathematical definition of what we mean for a function to be continuous at a particular point corresponding to x equal a. Our intuitive definition that you can draw the graph right through your a value without lifting your pen off the paper is a nice definition to keep in mind, and it works most of the time, but we will actually see that in some bizarre examples that intuitive definition is really will mislead us. So just keep in mind that this is our careful mathematical definition of what we mean by continuity. And I'll show you an example later where our intuitive definition actually misleads us into perhaps thinking that something isn't continuous when in fact it does satisfy the mathematical definition of continuity. But we'll do that way later at the end of this whole section. Okay, I'm also going to write down a kind of shorthand definition, because this is sort of a long definition of what it means to be continuous at a number a, and oftentimes we shorten the definition in the following way, and let me explain the shortened definition. We say a function f is continuous at a number a, again at some value x equal a, if the following is true. And you notice that what's sitting here really looks like the condition 3 that we put down here. I guess I written it in the reverse order here, but it's really condition 3, and you might say, well, what about condition 2 and condition 1? We know that all three of those have to hold for the function to be continuous at x equal a, and here I just have condition 3 written down. But oftentimes we write the definition of continuity this way, where when we write the limit as x approaches a of f of x is equal to f of a, in this sort of inherent or assumed in this statement is that this limit exists. So we are assuming, as soon as we write this down, that this limit exists. And also assumed in this statement right here is that f of a is defined. So we're assuming by writing down f of a equals limit as x approaches a of f of x, we are assuming f of a is defined. So we often write just the third condition in our three conditions, but kind of inherent when we write this down in this statement, if we're saying the limit as x approaches a of f of x equals something, well then that limit must exist. And if we're saying f of a equals something, then we're assuming that f of a is defined. So it's just a shorthand way of writing down what we mean by saying that a function is continuous at a number a, and really all three conditions are within this single statement. Okay, the next thing I'd like us to do is to try to apply this more careful definition of continuity to some specific examples. Okay, so what I would like us to do next is to try to apply this careful definition of continuity to some specific functions. So let's turn to the next page, and we'll try to determine whether each function is continuous at the value x equal 3. So that's what we're going to concentrate on for these. And then later we'll sketch the graph to see what's going on with the graph and why it's discontinuous in terms of the graph and our more intuitive definition of continuity. But we are going to try to apply the careful definition of continuity. And remember, that means that for each of these functions, we're going to go ahead and check those three conditions that we talked about. If all three conditions hold, then the function is continuous at x x equals 3. If any one of the three conditions doesn't hold, then the function fails to be continuous at x equals 3. So let's go ahead and look at this one. H of x is equal to 1 over x minus 3. And I want to ask the question, is this function h continuous at x equals 3? So I just started on my definitions, on my conditions, from our definition. And the first thing I have to ask myself is h of 3 defined? So let's go ahead and think about that for this particular function. H of 3, well, if I plug 3 in for x, I get 1 over 3 minus 3, which is 1 over 0. And because we can't divide by 0, that expression is undefined. So the answer to this question, is f of 3 defined? No, a resounding no. That means that h fails the first condition in our careful definition of continuity. Do we need to check condition 2 and condition 3 in our definition of continuity? We do not. Remember that all three conditions must hold for the function to be continuous at 3. As soon as we find a condition that doesn't hold, we're done, and we can go ahead and conclude, therefore, h is not continuous at x equals 3, or we could say it is discontinuous at x equals 3. Well, just to get an idea of what's going on with this function graphically and why it is not continuous, why there's a break at x equals 3, we could go ahead and graph it. In order to graph it, you may want to look at the limiting value and try to figure out what's happening as we get close to x equals 3 from both the left and the right. So if you want to, you could go ahead and say, well, what happens to this function? I can't plug 3 in, but what would happen if I approached 3 from the right for this function h of x? And we already know it's discontinuous at 3. We're just going to try to graph h of x. Well, that would be the limit as x approaches 3 from the right, and h of x is this expression, 1 over x minus 3. So we're finding the limit as x approaches 3 from the right of that expression. And you might notice what's happening if x is something that is a little bit greater than 3. We're putting in things like 3.1, 3.01, and so on for x. Notice the top of this fraction stays fixed at 1. I'm going to put a little arrow here. But what's happening to the bottom, as x gets closer and closer to 3 through values that are a little bit larger than 3, such as 3.1 or 3.01, when I subtract 3 off, I'm getting a very small number. 3.1 minus 3 is 0.1 or 1/10. So I am getting a very small number here, and in fact it's a number that's going to get smaller and smaller as x gets closer and closer to 3 from the right. Is this difference here, x minus 3, going to be positive or negative? Well, if I'm approaching from the right and x is a little bit bigger than 3, such as 3.1, when I subtract 3 off of that, I get a positive 0.1. So something that's getting smaller and smaller, but positive. And we've talked about this kind of limit before. If the top is staying fixed in a fraction and the bottom is getting very tiny, like a 1/10, 1/100th, when you invert and multiply those fractions, you're going to end up getting something that's very large in size. The smaller the denominator gets, the larger the fraction gets. The overall sign would be something, so the overall fraction is going towards infinity in size. And the overall sign, since I have a positive 1 in the top and a small positive number in the bottom, would be a positive infinity. So if we start thinking about this graph, what we're really saying is that as we approach 3 from the right, the outputs are going up towards positive infinity. And the only kind of graph that could work for that would be, if we're looking at a graph that's continuous at other points, would be a graph that's sort of screaming upwards so that the y values are going up towards positive infinity as we get closer and closer to 3 from the right-hand side. Let's now look at what's happening as we approach 3 from the left. That will help us to graph the function to the left of 3. If I approach 3 from the left of h of x, that would be the same as saying we're looking for the limit as x approaches 3 from the left of 1 over x minus 3. That's my h of x. Let's see if we can decide what's happening. Remember, if x is approaching 3 from the left, then my x values are a little bit less than 3. We're putting in things like 2.9 or 2.99, values that are a little bit smaller than 3. Well, the top of this fraction is still staying fixed at a positive 1. If you think of something like 2.9 minus 3, you notice you get negative 0.1. The size of that denominator is getting very small, smaller and smaller in absolute value. But what about the sign? Is it a positive denominator or a negative denominator? And I can see if I did something like 2.9 minus 3, I would get negative 0.1, and so it's going to be something that's small and negative, getting smaller and smaller in absolute value, but negative in sign. If the top of a fraction is fixed and the bottom is becoming tinier and tinier, again, the overall fraction is blowing up in size. It's getting to have an absolute value that's larger and larger and larger. What about the sign of this infinity that my fraction is approaching? I have a positive divided by a negative, so the overall sign would be negative. So as I approach 3 from the left-hand side for this function, the y values are going downwards towards negative infinity. So what kind of curve would fit that? It would have to be a curve that's diving downwards like this, so that the closer I get to 3, the farther down I have to go to hit the graph and go over to the y-axis. And the y values, the output values, would be marching down towards negative infinity. What does that mean is happening right at x equal 3 in terms of the graph? If the curve is going upwards as we approach 3 from the right and screaming downwards as we approach 3 from the left, that means that right at x equal 3 we would have an asymptote, a straight line that the graph is getting closer and closer to. And in this case, because it's a vertical line that my curve is getting closer and closer to, it's referred to as a vertical asymptote. Vertical asymptote at x equal 3. And in fact, the equation of a vertical line is x equal to a constant. So the equation of the vertical asymptote is the equation x equal 3. So this is what my graph looks like, and now we can kind of look at this function. We said that it was discontinuous at x equal 3. Can you see that from the graph? Well, sure. If I tried to draw this graph, you notice that because there's this gap and the function's undefined at 3, there's a vertical asymptote at 3, I can't draw the graph without lifting my pen off the paper to get to the second half of the graph and draw that over here. So I have to lift my pen off the paper right at the value x equal 3, and so from our intuitive definition of continuity, the function is not continuous at 3. So we've done both in purple here, we did the careful definition of continuity and showed the function was discontinuous at 3, and now we've graphed it. Of course, that's quite a bit of work to graph it, but that would be another way of at least intuitively saying that there's a break in the graph, and so it is not continuous at 3. Okay, let's go ahead and look at part B. In fact, what I would like you to do is to try to apply the careful definition of continuity to the function g of x. It's one of these piecewise functions. It's equal to the rule x minus 1 whenever your inputs are less than 3, and it's equal to x plus 1 if your inputs are greater than or equal to 3. So try stopping the video and see if you can go through those conditions. Remember, the first condition is you want to check and see whether g of 3 is defined. And if it is, then you would go on to the other conditions. You would check to see whether the limit as x approaches 3, that overall limit of g of x exists. And if that turns out to be true, then you would check the third condition and you would ask yourself, well, are those two things equal? Are the things in condition 1 and 2 equal to one another? So take a moment, give that a try, and then we'll go ahead and go through it together. Okay, let's try to answer each of these questions together. Of course, if we find a condition that doesn't hold, we get to quit because all three conditions have to hold for g to be continuous at 3. So first of all, let's ask, is g of 3 defined? Well, what would g of 3 be? We have to go according to the rule. And remember that my x value is 3, that's my input value. So we go over here and we say, let's see, if x is less than 3, we use this rule, but x isn't less than 3, it's actually equal to 3 in this case. And notice that if x is greater than or equal, in this case equal to 3, we use the bottom rule. So yes, it is defined, and to find g of 3, all we would do is use this bottom rule, and that's because in our case, we're down here in this part of the domain where x is greater than or equal to 3, in this case equal. So I'll go ahead and plug 3 into this, and replacing x with 3, I would get 4 as an output value. So yes, g of 3 is defined, and the output value corresponding to x equal 3 is a y value of 4. So condition 1 holds. That's great. We'll go on to condition 2 and see if the limit as x approaches 3 of g of x exists. Well, because of the way that this function is split up, we have one definition to the left of 3 and another definition for g of x to the right of 3, another rule to use to the right of 3. It makes sense to answer this question about whether the overall limit exists by looking at the left-hand limit and the right-hand limit separately. So what I'm going to do is say, well, this limit, overall limit, will exist only if the left and right-hand limit exists and agree with each other, are equal to each other. So let's look at the limit as x approaches 3 from the left of g of x. Well, remember then we are putting in values x that are a little bit less than 3. So we're looking at inputs that are less than 3 because we're coming into 3 from the left-hand side. Well, which rule do I use when I'm talking about x's that are less than 3? Notice according to my definition of g of x, that means I use the top rule, x minus 1, in place of g of x. And that's just because I'm doing a limit from the left, and so my x values, the things I'm plugging in, are less than to the left of 3. So for these values that I'm limiting through, I can replace g of x with this top rule. G of x is the same thing as x minus 1. And notice I put parentheses around my expression. I'm taking the limit as x approaches 3 from the left of that entire expression. So it's important to put those parentheses in there. Otherwise, it looks like you're doing the limit as x approaches 3 from the left of x, and then you're subtracting the number 1 from that limit. And that's not really quite what we're doing here. Okay, so g of x, same thing as x minus 1 for these particular x values that are less than 3. And now I want to say, well, can I find that limit? Well, yes, I can. What kind of function is this? This is a polynomial. And remember that to find the limit of a polynomial, we get to use direct substitution. So I just go ahead and I replace x with a number it's getting closer to, namely 3. And I end up getting a limit of 2. So as I come in from the left-hand side for this function, the output values are collecting around the number 2 on the y-axis. Well, let's go ahead and see if we can do the limit from the right. Let's see if I can fit it in here. The limit as x approaches 3 from the right-hand side of g of x. We want to find that limit. Well, remember, if x is approaching 3 from the right, that means that x is a little bit greater than 3. I might be putting in something such as x equal 3.1, 3.01. They're values that are to the right of 3, so they're a little bit greater than 3. So we have to ask ourselves, for these x values, which rule do I want to replace my g of x with? When x is greater than or equal to 3, in this case x is greater than 3, I'm supposed to use the bottom rule. So I'm supposed to replace g of x with x plus 1. So for those values, and let me see if I can get a blank piece of plastic so that I can get a little bit more room here. So for those values of x, I'll be finding the limit as x approaches 3 from the right, and I can replace g of x, this thing, gets replaced with x plus 1. I use the bottom rule for g of x. Then the question becomes, can I evaluate this limit? Yes, I can. Again, this is a polynomial. So I can go ahead and use direct substitution. I replace x with the number it is approaching, namely 3, and I get an output value of 4. So as I come in from the right on my graph, I'm not quite sure what the graph looks like yet because I haven't bothered to graph it, but the outputs are collecting around the number 4. Now remember that our question in condition 2 was, does the overall limit as x approaches 3 from both directions of g of x exist? And for that overall limit to exist, we said, well, the limit from the left and the limit from the right have to exist and agree. Do they exist? Yes. The limit from the left is 2. The limit from the right turned out to be 4. But do they agree? Are they equal to each other? Unfortunately, no. That means that as we're approaching 3 from both directions, the y values are not collecting around one number on the y-axis, they're collecting around 2 different numbers. And so the overall limit does not exist. So unfortunately, this number, the limit from the left, a little arrow there, and the limit from the right, the 2 and the 4 do not agree. 2 is not equal to 4. And that means that the limit as x approaches 3 of g of x does not exist. So the answer to this question would be no. Well, what does that mean about the continuity of g of x? Remember that for g of x to be continuous at x equal 3, it has to satisfy all 3 conditions in our careful definition of continuity. It did satisfy condition 1, but it did not satisfy condition 2. Therefore, g is not continuous at 3. So we can say, therefore, g is discontinuous at x equal 3. Do I have to check part 3? No, I don't have to check because we've already found that g does not satisfy condition 2. It has to satisfy condition 1, 2, and 3 in order to be continuous at 3, and it already failed condition 2, so I don't have to bother to check condition 3. Now if you want to, you can go ahead and graph g of x in order to get an idea graphically of why this function is discontinuous at 3. And to do that, well, it looks like the line y equal x minus 1 when x is to the left of 3. Let's see, x minus 1, that would be, if I graphed, I'm graphing y equal x minus 1. If I were to graph that, it's a straight line. It crosses the y-axis at negative 1. And it has a slope of 1, or 1 over 1, so I go up 1 and over 1. And it looks like I would end up with something that would be the left half of that line, because I only want the portion of the line corresponding to x strictly less than 3. That means I have an open circle right here. And so that would be graphing this portion of g of x that is to the left of 3. If you want to graph the portion that's greater than or equal to 3, it would look like the line y equal x plus 1. But again, we'd only want the portion of the line that's to the right of 3. that line would have a y-intercept of 1 and a slope of 1. So let's see, at 3, that would give me an output of 4, has a slope of 1, I go up 1 and over 1, so it looks something like this. And I would have a solid dot here right at 3. That's because we use this line, y equal x plus 1, if x is greater than or equal to 3. It's this strict inequality here. So, I'm sorry, this greater than or equal to sign here. So if you graphed g of x, it would look like this. And is it true that the graph also shows that this function is discontinuous at 3? It is. We can't draw the graph through x equal 3 without lifting the pen off the paper. There's a jump in the y values. You can also see here more clearly why the limit from the left, the values of y were getting closer and closer to 2, so the limit from the left was 2, whereas the limit from the right, as we get close to x equal 3 from the right, the y values are collecting around 4, so we said the limit from the right was equal to 4. And the fact that these two one-sided limits are different is creating this jump in the graph. So it is not continuous at 3, and that's in this case because there is a jump in the graph. In our first case, it was because the function wasn't even defined. There's no point on the graph corresponding to h equals 3. Okay, let's go ahead and look at one last example.